Welcome back, everyone. Before we actually jump on the actual topic on advantages of simulation of an embedded hardware, I would like to quickly talk about recent changes which has happened in ARM licensing. So please bear with me. This is not it's not anything on the commercial webinar. It's pure a technical webinar, but this is the right platform to find out that important message. Whatever ARM has done the changes recently. So I'll just share my screen. So hope my screen is visible. Here, for the benefit of the team who is not aware what is gold, I believe the attendees of this webinar is very well conversant of for this Keil software for probably 8-bit, 60-bit, and maximum 32-bit processors for ARM. So Keil is a software solution from ARM. Similarly, there is also one more software toolset given by ARM, and it is called as ARM Development Studio. Okay. So ARM Development Studio is basically a single software. I did conduct a webinar on this, a technical webinar on this quite some time back. So ARM Development Studio is the toolset again with ARM compiler, but it is a single tool suite which supports all the ARM processor cores from the lower end ARM 7, ARM 9, Cortex M to higher end Cortex 8 32-bit and 64-bit processor core. Okay, so Development Studio is that one single tool set, and earlier the licensing was a normal, like we have two types of licensing: node lock standalone license or a network license. We call it as floating. Now has come up with something called as user-based license. The user-based license, there is no concept of floating or network. It is based on only on how you activate the license. You'll be getting one a serial number kind, and based on that, user can activate the license. It's the most um, reasonable. It's been priced very reasonably. If anyone is interested in UPL Gold, you can please send out an email to my mail ID, which I'll share it at the end of the webinar. So now it was just a quick um, uh, update on the licensing policy, and ARM will be implementing the same user-based license UBL for even Keil as well, which will be from next year July onwards. So yeah, now let's quickly jump to our webinar. So coming to advantages of embedded simulation. In fact, I had did one more presentation on the similar lines on simulation models offered from ARM, basically for their ARM processor cores, how simulation models will help the users or customers to get the product on market well before the time. Basically, whatever commercial solutions customers tend to go for by paying the amount, high cost or low cost, they invest, in other words, is because it's very critical to get the product what to develop on market or to the market on time, because it's a competitive world and many companies can tend to work on the same product, and that time the company or whoever releases the market, whoever releases the product to a market before we capture the market, we have more profit margin, more percentage of profit. So that's the reason why customers, companies tend to invest on commercial solutions. So I did talk about simulation model. If I tell you the earlier way of development, which embedded engineers used to do, is to first develop the hardware, decide on the PCB or Gerber or whatever it is, and once they get the hardware on hand, maybe a POC, even in the lower end, not the completely designed board, just in the processor and the clock circuit and everything. After that, they'll start developing the software. So the software team who is uh, responsible for generating the code, developing the application software for that product, it has to sit idle until the hardware team gives them the a kind of a role model or a hardware board which will help the user software team to develop the code. But to avoid this gap, so these simulation models will come into picture, and these simulation models will parallelly make the hardware team and the software team work in parallel, and thereby we can reduce the time the software team has to sit idle as in the earlier scenario. So on the parallel hardware team will work on developing the hardware, and software team will start developing the code because they'll be having the model of the hardware, what is the actual requirement, and they'll start developing the code. And because there is no hardware, they have to test that code right somewhere to see that the code does work as fine as expected on the hardware. So simulation models, the users versus users, development users or software development team used to test their code on the simulation model. Okay, so that was just a background, a quick recap of the simulation model webinar which I had given last year. And today we will be talking about the same thing, maybe a advanced version of this simulation and how it has been implemented in Keil ID. So coming to Keil simulator, I'm sure quite pretty sure that many of the customers might not have used Keil simulator at all, because users tend to develop the code and try to test it on the hardware like a traditional way of development. But Keil offers a very powerful and a full-fledged simulator which is seamlessly integrated in Keil IDE. Like if you are taking case of Eclipse, in the Eclipse, sometimes you have to open the development same IDE for development and another IDE again for debugger. But here is the single IDE, both for development, for programming, building the project, building the code, and testing the code as well. Both. Okay, so this simulator is integrated in 𝝻vision debugger, which is Keil 𝝻vision GUI front end. So this can simulate the behavior of your target application. Okay, so you can test, this development team can test their application even before they get access to the hardware. And when I mean testing the code, because when it's come to the real-time application, it's not just we'll be writing some GPIO code or something like that. It's a lot of sensors, UARTs, interrupts, communication peripherals, all will be involved, SPI, UDC, all the peripherals, timer, everything will be involved. So when we tell that Keil provides simulator, so Keil has the facility to even test all these peripherals without on a virtual target. Virtual target means there is no target, but on a simulator, it's a simulated version of your target. We can test the code. Okay. How Keil supports this with lot of features, which I'll be explaining in this slide. And at the end of this slide, I'll be showing you also the practical demonstration of the simulator, showing you the how this some of the communication peripherals can be simulated, and then you can have the Q&A session. So please, the team who is part of this webinar, please feel to put the questions, whatever you have in the chat window. So at the end of this session and after demonstration, I'll come to the FAQ. So how it does, I'll simulator gives the debug functions, inbuilt debug functions. I'll show you also to how to find these debug functions. It's all given in the online help of the Keil IDE. Then 𝝻vision simulator also helps you to simulate, as I told, all the communication protocols like UART, I2C, SP, and CAN. So you may ask me, not only that, you can also simulate interrupts. So thought may come to your mind. How is she telling that you can simulate all this? Because these peripherals can only be simulated when the data comes on a specific pin of a controller, probably. Suppose if you want to simulate, you have to, if you want to ensure that the data what you sent from the processor has gone out of the processor to UART, how do you test in hardware? Usually it is sent through the transmit pin of the UART. We usually use a probe or a CRO and see whether the data is being sent, data is made available on the TXT pin. So without connecting any hardware, how do I simulate this UART? How will I simulate the code on the communication peripheral? So that is how the Keil, how the Keil has implemented. I'll come in the next slide. So how it is done with the help of a signal functions. So what are signal functions? Signal functions are something which will execute in the background of the IDE. I mean your info program, your application, what your software code, what you developed in Keil BT, running on the simulator, Keil simulator in the background, signal functions will be executed. Okay, so whenever you're using signal functions, there should be a delay. There should be some delay so that the execution of the background function stops and in the foreground your code can execute. Both has to execute maybe in orderly manner or with some delay. So without delay, signal function cannot be implemented. The signal function, I'll show you also how the definition and all, how it is written. Signal function starts with the keyword signal. So this is how it starts. Signal functions begins with the keyword signal. Okay, it should not have any it should not return any value. You can pass value to the function. So you can, when I tell function, it's like similar to a C function, like a normal C function, right? But only this function starts with the keyword signal. Okay, and this cannot be written as part of your program. Remember, these signal functions cannot be defined as part of your program. It has to be defined as part of the simulation. So how it can be defined, where it has to be defined, all those I'll show you when I show the demonstration. So in this case, this function, what it does, stuff SO in. So this stuff SO in is one function. Here, what I'm doing is I'm trying to simulate the receipt of the data through UART. So I'm trying to simulate if the UART is present in my processor and if some data is coming, I have written in the code that once the data comes from the UART, what the processor has to do the processing of the data, but the data has to come to the UART. So through the signal function, I am sending the data to the UART. So through the UART, I am getting the value A. So UART is receiving the character A, 41 hex code. Then there is a delay. So this delay can be T-watch. We have different watch here. We can give the watch for the machine cycle, watch for the seconds, give the delay for the clock cycles, but there should be some delay has to be good. Okay, I'll explain all this in detail when I demo. So suppose, which I'll be demonstrating also this. Here using signal function, here we are trying to simulate ADC, analog digital ADC, analog to digital converter. So in analog to digital converter, as the name suggests, it takes the input as analog and it gives that particular block is the output as a digital. Okay. So now in the program, how can you feed the input to the analog ADC? Because the team will appreciate that the data has to be given through the pin of the microcontroller, through the analog channels of the processor. You have to feed in analog input. Then only ADC, what you have initialized in your code, will read that data and it will convert to the digital data, and that you can use it for further processing or whatever further the code is required or the product requires application. But here, without even connecting any hardware, without giving input to the analog pins of the controller, we can still simulate ADC. How it is done? So you can see here. This is a ADC converter block. This is true for any processor, but you have to ensure that whatever the processor you have selected in Keil is well simulated in Keil IDE. The current version, MDK version 5, what it is running, given by ARM, does not have simulation support, but the MDK version 4, 𝝻vision 4, has a simulation support for the earlier devices that ARM had supported in Keil MDK. So here, when you open this ADC converter dialog box, I'll show you how to, from where this option can be accessed. This is your control register. Okay, this is to start your conversion. This is the clock for the ADC, and all the additional options or features for that ADC. Okay, sorry. So here, to which channel I'm giving input, I can suggest. Suppose this particular ADC block has, I can give input through 4 channels, 4 inputs. Okay, so one at a time I can feed input to all this. So there are ways, either you can directly type in the value there, analog input 0, 1, 2, 1, 3, and you can see that digital data will be shown on the ADTR. But every time you have to keep on entering the analog input value to see the ADC digital data. Instead of what we do, we will write a signal function as I showed in the previous slide, and we will ensure that signal function will generate an input to an ADC. Okay, and that input will be given to the ADC, and then ADC, the code what I've written to initialize the ADC, will do the digital data conversion, and it will show more the digital data here. So similarly, we'll see all this in demonstration. Similarly, we can also simulate the digital input. So when does the digital input useful? Especially for the interrupts. So interrupts. So whenever you want to simulate the interrupt can be from the peripheral, or it can be an external interrupt. It can be anything. And an interrupt is generated through the pins, and the particular pin of a processor goes high or low, only interrupt is generated. So through this pins option, you can see, because the interrupts are usually multiplexed with the GPIO pins of the microcontroller. So you have to go through the architecture manual and see which particular port pin is multiplexed with the interrupt, and that particular pin you can make it high or low, so that that particular interrupt will be generated. One thing to note, when you're connecting your hardware, you can see when you open the GPIO block, this pins option will not be there. Pins option is specifically given for simulation of your code, specifically and purely. Similarly, you can see logic analyzer. So whatever the analog input, which I was explaining in the previous slide, if I'm generating that analog input through a signal function, then I can also simulate that analog input, how my function is generating the input. I can also block that. I can also draw in, you can see that in the logic analyzer. Basically, logic analyzer is used to watch your variables or any data that you have in your program defined in the graphical format. Okay, and you can also see if you place a cursor plus specific point in the logic analyzer, it will also take you to the point in the code which made this transition in the signal, and it can be all this. You can do it. When you're using with the Cortex M, you can also see real-time logic analyzer data information through the trace feature. So that webinar I have already done. So you're not talking about that here. So through logic analyzer, we can also watch the signal functions or any input time generated to the signal functions. Okay. So you see here what VT register. VT register are called as virtual register. So as the name suggests, these registers are not present in the microcontroller. They are not also part of the processor. But ARM has given a set of virtual registers for each processor you select for the project development. When you create a project, you'll be selecting a device. So based on the device what you have selected, ARM gives a set of virtual registers. Okay, that's so using those virtual registers, we can write a signal function, and we can also simulate the interrupts. This is how your logic analyzer looks. So suppose here, this is the input what I have given. If I write a C function, which will generate a staircase waveform as an input to the ADC. Through C function, I can generate a staircase waveform. This will go as an input the ADC block. So it will also show what is the input that I have generated. Logic analyzer, you can see all this information. Code coverage. Code coverage also you can see in simulation. Um, the time taken for the execution of every function, you can see that. System analyzer. System analyzer is basically, this is not available in simulator, but this when you use with the JTAG debugger, if it is used with the Ulink Plus, it's a JTAG debugger with which you can do power measurement of the application. And system analyzer, if used with the Ulink Power Plus with the trace feature. This is specifically for Cortex. Okay. If it is an RTOS based, you can also see without any JTAG debugger also. And RTOS thread events, RTX, RTOS, any tasks or threads you have defined, the status of them, you can see that in system analyzer. This is how the system analyzer looks. You can see all the exceptions. You can see all the RTX, RTOS events, the threads which are defined. This read to data watch, which is a trace option. If you're connecting Ulink Plus, you can also see the current consumption. This is with the system analyzer. Okay. Now I'll show you with the Keil IDE. Okay. So this is my microvision project. So I have a excuse me. I have a sample project given my myself. So you may be wondering why I'm not able to see that sample project. This is specifically for NC1760 board, which was made actually by ARM. It is based on M3 based microcontroller from NXP. So you may see if at all we are opening Keil ID from your end and you want to see, we may not see that if at all you're using MicroVision 5. For that, you have to download the legacy pack because LPC1668 was the legacy device. This device was supported in MicroVision 4 first. To get this device listed in MicroVision 5, you need to install the legacy pack. Then you'll be able to see this. In the ARM, you can see boards option. Otherwise, you don't see the boards option at all. So boards, you can see boards from various vendors, Flashling, Atmel, Embedded Artist, Embest, Freescale, High Luminary, Microsemi, all these board vendors you can see. So now we'll go to Keil, MCB1700. So this project Blinky ULP, this is for Ulink Pro, connecting the JTAG debugger Ulink Pro with the Keil board. I'll be testing this program in the simulator to show you the features of the simulator. You just build a project, and if you go to project options for target in the debug, you see debug underscore sim.ini. So this, as this Blicky project is basically, let me explain you, this is actually for controlling the onboard LEDs on the board using the onboard potentiometer. And that is potentiometer, as you know, it's a variable input you can give, and it is connected to the ADC. Okay. So through this signal function, here we are trying to simulate the ADC on particular peripheral I'm showing. So I'm using the signal function to generate the input. So I was telling in the presentation that signal function should not be part of your actual code, what you develop here. Sorry, this is your actual C code. Here we cannot write signal function. Signal function has to be part of the simulator. So for that, if you edit this, you can see the signal functions is the INI file. So whenever you want to write any specific feature for simulation of the peripheral, simulation of interrupt or anything, you have to write an INI file, not INI extension. whatever commands you give here, as soon as you enter the simulator, ID will just execute those commands, and then the code will processor will execute and come to the main function. In the simulation only, I'm telling. Okay. So this is the C function which I have written in INI file. So you can see it starts with the word signal. Function name is analog. Here I have given the parameter as float limit. And as I said, it should not return any value, so it's void. Like a normal C function, I'm defining a float variable. Okay. So the limit here is, this is 3.3 volts I can give, because input for the ADC can go up to 3.3 volts. So limit is that this have to give a limit when I call this function like a normal C function. Until a function is called, that function will not be executed, correct? So that function I am calling here analog 3.3. Okay. So here, just to show whatever the input limit you have entered, it will just print on the command window that analog 3.3 entered. Now inside the while loop, I'll start. I'm actually in this program, I'm generating a staircase waveform to the as an input to the ADC. So you can see it starts from 0. And when the volt, it starts from 0 and it is less than limit, which is 3.3. So this volt value is given to AIN2. So in my board, the input to the potentiometer is given through the channel 2 of the ADC. So to access the channel 2 of the ADC, I have to use the register, virtual register AIN2. Suppose I want to access the channel 3, I have to give AIN3 like that. So these are the virtual registers. So virtual register is there for each pin of the microcontroller. So now you can understand that through virtual registers, you can get access to even the pins of the microcontroller, which is not possible in your actual code. Okay. Then we are giving the delay here of cycles T watch. Then I'm incrementing this volts by 0.1. It's a staircase. So it will go 0, 0.1, 0.2, 0.3, like that. It goes up to 3.3. And once it goes to 3.3, again I decrement to 0. So this is how this function executes. It just generates a staircase waveform to the, and we feed it to the virtual register AI2, which happens to be the input for ADC. Correct? So this I'm giving it, and now I'll enter the simulator. So once I enter the simulator, you can see here it's analog 3.3 entered. It indicates my signal function is already running. Because as I told, as soon as you enter the simulator, first thing the Keil does it will execute all the commands, anything you've given in the INI file, and then it comes to the main function. So now it's come to the main function. This is my program counter. Because it's a C function, I can understand, but sometimes we also tend to do the mistakes. Okay. So there is also a compiler for this INI file. So that will get it from debug function editor. This is your function editor. So if there is any error, it shows. If there is any error, now there is no error because the signal function once activated cannot be reactivated. That is one limitation. So only it's telling signal is already activated. Otherwise, there is no error in this function. Okay. Now we will see. Before that, I'll show you directory VT register. So here you can see these are all the virtual registers which are made available for LPC 1768 Cortex M3 microcontroller. So we have crystal, serial clock, USB. These are all for GPIO, port 0, port 1, port 2, port 3. These specifically give access to the port 0 pins, port 1 pin, port 2, port 3. SIM is not in for simulating your receive of data. S not out is for simulating the transmitting of data. This has 3 words, although you can see even for CAN, you can see for each bit also, you can simulate. CAN bus 7-bit. 2 CAN buses are there. It has SSPI, SPI, I2C, it has analog input. Our interest is this, AIN2, is where I have to give the input. And I wanted to show you the debug functions. So before that only, okay. Complete users guide, microvision users guide, debugging. Here you can see debug functions, predefined functions. So these are some of the predefined functions of Keil simulator. You have for all this trigonometric thing. If you want to read some specific memory location and write it to some other memory, read byte, read word, write. So you have also the R watch, AT watch, S watch. So user functions, signal functions. Signal function, it has to start with signal word. The same thing is taken here. Right? So this is the functions. Okay. Now we will go to peripheral ADC. This is my ADC peripheral of this controller. You have for each channel there is one address which is data register. So this is actually 8 channel. So for each channel you have a associated data register. You can also see the result. Okay. Now when I, because the signal function is already started running in the background, I can, when I give the run, you can see AI into changes, because in my INI file I have given the input to the AI into. So you can see here. It actually um, has to, it will show the input, analog input, whatever I've given, or we can also see AI into. So you can see here, you can see the green one. So green one is my AI into. So you can see the staircase waveform. So this is, if I write a C program, C signal function to generate a sinusoidal wave, yes, you can also, it will generate a sinusoidal wave. There are a lot of examples given by ARM itself for generating sinusoidal, triangular wave, square wave, rectangular wave, anything. So this is here, see how it goes. Steps of 0.1, it goes to 3.3 and it comes down to 0. And here result is shown in the 2. This is your ADC. So I'm not only able to simulate ADDBG is a variable which holds the digital data. AI into is the signal what I'm feeding into the processor ADC. And we can also see here, it shows the printf value, digital data. Whatever the digital data it shows, this also shows. Okay. So similarly, we can also simulate a lot of things like you have system viewer. Um, so UART0, UART1, PWM, I2C, SSP, for peripherals, you can see if interrupts are defined, you can also see the interrupts defined. All those, for each peripheral, there is a window like this, it comes. Okay. So whenever you want to know what are the virtual registers for the specific process, you just type dir. It will only tell you with dir what all I can give: function, define symbol, a bit function, user defined function, signal, line, module, public, VT register. As soon as I give V, it will give me the virtual register. So similarly, you can also simulate the UART. Here I have shown you the simulation of ADC. You can also simulate the UART in a similar way, or even the communication peripherals. So I don't know whether a team here who is attending part of this webinar should be well conversant with the Keil. If not, or the team wants to start with Keil. So the first step would be to download the Keil software from keil.com, or you can download from developer.rm.com, the same site which I showed. Okay. So developer.rm.com shows all the information, technical information about the tool sets offered by ARM, the compiler, linker, assembler, simulator, debugger, whatever is there. So you can start with that. And I believe there is no question. So I can give you, it's 3:41. I can give 5 minutes for if anyone has a question, you can ask. I can send mail to, maybe I'll write it in slide. Any questions or technical clarifications or any sort of information you want on the software, compiler, simulator, or even a debugging thing, facing some issues, you can please reach out to me, Geeta@gsasol.scale, and this is my phone number, 9343756802. Okay. I forgot to do my introduction. I work as a director of tools and take care of both the technical and the commercial part. I do support on the technology, as well as I drive the business for software tools in India. So there are no questions. Or anyone has a question? Or if the team has any better topic for me to cover technical on the software, any specific feature or option, please send mail to my mail ID. I'll be happy to do the webinar on that particular topic. Every month, I conduct a technical webinar on software solutions offered by. So I believe there are no questions. So thank you, team, for your time and making it up for the webinar. I'll see you soon in the next webinar. Thank you.